Suppose f of x is a function that satisfies all of the following. F of x is continuous on the closed interval from a to b. It is differentiable on the open interval from a to b, and f of a equals f of b. Then there is a number c in the open interval from a to b such that f prime of c equals 0. So in this picture here, the function is indeed continuous on the closed interval a to b. The function is actually continuous at a and it's continuous at b. There are no breaks in the function. The function is differentiable on the open interval from a to b. Actually, the function is not differentiable at a and it's not differentiable at b because we have sharp corners at a and b. We can't imagine constructing tangents there. The curve is not smooth at points a and b. But that's okay. Both those conditions are satisfied, and you can see f of a equals f of b. Now there is a number c. Now there could be more than one number. Actually, there's two numbers in this picture, such that the derivative is 0. So there's actually two possible values for c here. We have two horizontal tangents. Now we're going to consider three cases. The first case is where f of x is a constant k on the closed interval a to b. Here is a graph of our function. Now k happens to be a positive number in this picture, but of course k could be a negative number or it could be 0. But we can see that it's continuous on the closed interval a to b, and it's differentiable on the open interval a to b also. The derivative of a constant function is 0. So we want to prove that there is a number c between a and b in the open interval ab such that f prime of c equals 0. Well, it's clear that we can take any number between a and b. Now let's consider a function where there is a number d in the open interval ab such that f of d is greater than f of a. Now, since f of x is continuous on the closed interval ab, we can use the extreme value theorem, which is stated in a previous video. It says that there will be an absolute maximum of the function f of x on the closed interval ab. In this picture, this point is the absolute maximum. Let's suppose that our absolute maximum is called c. Now, since f of a is equal to f of b, f of d, which is some point in ab, is not only greater than f of a, as we stated from the outset, but it's greater than f of b as well. So that actually tells us that the point c, which gives us our absolute maximum on the closed interval ab by the mean or the extreme value theorem, but c also gives us a relative maximum. Look at this picture here. Suppose f of a is not equal to f of b, and then we can't apply Rolle's theorem. Well, we can see that from this picture that f of d is indeed greater than f of a, and by the extreme value theorem, the absolute maximum occurs at b. Okay, we have an absolute maximum, but you can see it's not a relative maximum. We can see that for an open interval containing the point b, f of b is not greater than or equal to f of x for all x in this open interval. Whereas in this situation here, if we take an open interval containing the point c, then f of c will be greater than or equal to f of x for all points x in this open interval. So that's why property 3 is needed to establish that our absolute maximum is a relative maximum. Okay, now we're given that f of x is differentiable on the open interval ab. Now c is some point inside the open interval. After all, d, we are stated at the outset that d is a point in the open interval. If c was not in the open interval, then c would be one of the endpoints, but that contradicts the fact that c is meant to be a relative maximum. See, we already know that there's a point D such that f of D is greater than these two. Okay, so C is in the open interval, and that means that f prime of C exists since f of x is differentiable on the open interval. And now we can use Fermat's theorem, which tells us that f prime of C is 0. So we've proven Rolle's theorem for the case where there is a number D in the open interval AB for which f of D is greater than f of A. The third and last possibility is that there is a value D in the open interval A to B such that f of D is less than f of A, and the proof of this is very similar to the second case. So if you think about it, there are only three cases. The case where the function is equal to a constant which we call k, the case where there's a number D in the open interval A to B such that f of D is greater than f of A or f of B, f of A is equal to f of B, or the case where there's a point D in the open interval A to B such that f of D is less than f of A, which also means it's less than f of B. Finally, I just want to emphasize why the first condition is important. Here's an example of a function where the first condition is violated. F of x is not continuous on the closed interval from A to B. As a matter of fact, we have discontinuities at x equals A and x equals B. The second condition is obeyed. F of x is indeed differentiable on the open interval from A to B, so if we ignore the points A and B, we have a smooth curve. And we see that f of A equals f of B. Here's f of A and here's f of B. So we have between A and B a curve that approaches asymptotically the vertical line x equals A and the vertical line x equals B. But we can see clearly that there is no number C in the open interval from A to B such that the derivative is 0. At no point on this curve do we have a horizontal tangent.